here. If this changed the whole moment of inertia. That is what is the mass related to. But if I put this and a hollow one with the same mass, you think that they will move the same way? No. Put a bowling ball and a ball that is empty but has the same mass. Will have the same type of rotation? No. So, in addition to the mass, the ability to rotate or the tendency to resist any rotational motion will depend also on the distribution of the mass. Besides the mass itself, the distribution that is the mass here along the radius. Those two things will be called moment of inertia. And let me just explain that through here, through the Newton law. Let's say that I apply the force to here. So sigma F, imagine that this is a piece of mass N, and I apply the force. So if I want to find the torque, the net torque is given by just this F. So it will be by definition R, which is the distance from here to here, time the force, which is the net force. In this case we call sigma F because that's the only force, so that is sigma F, times sine of what angle in this particular case? What is the angle between them? 90 degrees. So we get 1. So R times sigma F. What is sigma F? Sigma F. What is the net force in physics? Mass time acceleration. So we get R times mass times acceleration. And what is the linear acceleration? What is the linear acceleration in terms of alpha? Alpha R. So I get R times M times alpha R. What do we get? mr squared times what? Alpha. So if this is the Newton law for linear motion, sigma F equal ma, sigma tau is for rotational motion. I said that F is analogous to T. I go to here, alpha is analogous to A. What will be analogous in this particular case to the mass? If alpha is analogous to A, F is analogous to tau, what will be analogous to N in the Newton law? This product, mr squared. That product, mr squared, will be called for a particle I. And this is the Newton's second law for rotational motion. What is the meaning of I? This is the measure of inertia, the tendency of all objects to resist a linear motion. This is the tendency of all objects to resist the rotation or the rotational motion, I. So I, for a particle, a single particle, which is related to N, and this is one of the most difficult things to understand in rotational motion, I. What is I? I, for a single particle, is mr squared. If I have too many particles, what will be? The summation of mi ri squared. For instance, let's say that I have this object. It's the same if this rotates like this, so depends on the axis of rotation. If the axis of rotation is with respect to, I will put this I. It's a scalar, but the moment of inertia depends on the axis of rotation direction. So, look, this is the moment of inertia, the summation of mi ri squared. Let's say that I have this, and this is rotating like this with respect to here. What will be my moment of inertia? Let's say that this is here, the axis of rotation. What will be my moment of inertia? This is this, this is this, and this is rotating with respect to here. this is the distance from here to here, from here to the mass, will be called R1. And the distance from here to here will be called R2. This is M1, this is M2. How can I get my moment of inertia of that system, of this system, rotating like this? With respect to what axis? If this is X, this is Y, and this is Z, with respect to which axis is rotating, X, Y, or Z? X, Y, and Z. What is the axis of rotation? Parallel to what axis? If this is X, this is Y, and this is Z. Parallel. Assuming that this is X, this is Y, and this is Z. I put the axis of rotation like this is parallel to which axis? To Y. So I will put I with respect to Y. Find I with respect to Y. What will be? According to this formula, this is a system of discrete particles. I will be M1 R1 squared plus M2 R2 squared. This is the moment of inertia. This is like similar to the mass in linear motion. So the mass is not what is important. What is important is the combination of that, M and R squared, where R is the distance from the axis of rotation to what is the mass. Good. What about with respect to C? This is C. If it's rotating like this, with respect to C, it will rotate like this. Is that right? The moment of inertia, assuming that it's the same thing, instead of that, I put the moment of inertia like this. I mean the axis, sorry. The axis like this. I want to find I with respect to C. What will be? This is my axis of rotation. The system is, forget about this. This is the axis of rotation. It's rotating like this. What will be the total moment of inertia for that system, assuming that this rod doesn't have mass?